All right, Algebra 2, Section 5.1 is a nice continuation of what we were doing in Chapter 4. When we were just dealing with quadratic functions, now we're stepping things up a notch, and we're moving into polynomial functions in general. So it's important to understand that everything we're learning right here encompasses everything we did in Chapter 4, but we're taking it a step further. Okay, this first slide is a little boring. Sorry, guys. It's a whole bunch of vocab, which we really need to get down at the beginning of a chapter. So the first thing we want to define is a term that I'm thinking you guys have been using for a couple years here, a monomial. And hopefully you guys know that the prefix mono always means one, and then that nomial right there is just a way of writing a number. So a monomial is basically one number. That's how you can think of it. Now the formal definition, a monomial can be a real number or a variable, or the product of one or more variables with whole number exponents. That's a lot going on. But that word product is important. These numbers have to be multiplied together. There's no addition or subtraction in a monomial. So if you write that down, great. But you're going to learn what a monomial is by seeing it in action. So let's go through each of these in turn. A real number, it says, can be a monomial. So for example, 8. That's a monomial because it's a real number. So that's one example. Another example would be just a variable, like the variable n. That's a monomial. And then really, what this third thing is saying here is that it can be a combination of numbers, variables, and whole number exponents all multiplied together, hence the word product. So this is a little bit more telling of what a monomial might look like. It could be something like -5 x to the third power times y to the fourth power. Now that's much more complicated than the first two, but all three of those, 8, n, and then this -5 x cubed y to the fourth, are all examples of monomials taken one at a time. Okay, so now that we kind of have a sense for what a monomial is, we're now going to try to define the word polynomial. And again, hopefully you guys know a little bit about the English language right here, although I think this is actually Greek. The prefix poly means many, and then there's that nomial again, a way of writing a number. So a polynomial is basically many numbers, whereas a monomial was one number. Our more formal definition, a polynomial can be a monomial, or, here you go, the sum of monomials. And now with the word sum, we're now talking about addition, and then of course there can be subtraction as well. Let me come back to this idea in just a second here, and let's jump down to examples here. So again, you'll learn this better just by seeing it. Polynomials are multiple monomials added together. So for example, let me take a couple of those that I had before, n plus 8, that's a polynomial, everybody. Or there can be other exponents, and there could be subtraction involved. So you could be dealing with something like we saw last chapter, which would maybe be -2x squared minus 4x plus 7. That's a polynomial. And it can get even more complicated than that. It can have multiple variables going at the same time here. So we could see something like 11xy cubed minus, oh, I don't know, I'm just making things up here, 9x squared y to the fifth, and then maybe just a plus 3x to the eighth. It doesn't have to have a y in there. And then minus 7y to the second power. That would be a polynomial as well. So the key here is that with monomials, it's just one number, no addition or subtraction. But in the polynomial examples that we wrote down, you've got multiple terms, we call them, or multiple monomials being added or subtracted together. Okay, now, we like to come up with a naming system right here for naming different types of polynomials that are out there. So let's run through this quick list right here. I'm sure this table could go on further, but once you get beyond a fifth degree polynomial, I don't actually know, and I've never heard any specific names used for them. Okay, the first one right here, a 0 degree polynomial. All right, if we don't know what degree means, I guess maybe I should go back and talk about that. Degree means the highest exponent that you're going to see on a variable. I'll show you what that means in a second. So here you go. A 0 degree polynomial means it has no variables at all. That is basically what we call, everybody, a constant. So an example of a constant, 5. There you go. It has no variables to it at all. So that's a really lame example of a polynomial. A first-degree polynomial is one that's going to have your variable raised to the first power, and that's what we dealt with in the beginning of this year. In fact, that's what you dealt with in almost all of Algebra 1, and then we reviewed that at the beginning of Algebra 2. That, everybody, is what we call a linear function. So a linear polynomial would be something like 3x minus 1. You'll notice there, guys, we have an x, but with no exponent on it listed, we should know that's an exponent of 1. Whereas in that 5 up above, that's really an x to the 0 power because there was no x there. So when we talk about degrees, we're talking about the highest exponent that you see on your variable. That's 3x to the first, so that's why that's a first degree polynomial. Now, once we get into second degree, this should look familiar to you guys. That we just spent a whole chapter talking about, guys. That is called a quadratic function or a quadratic polynomial, and that's one that has x to the second power. So again, we saw a bunch of this last chapter, maybe something like x squared plus 5x minus 11. There you go. That's an example of a quadratic polynomial. Okay, on to some new stuff now. These three right here, guys, third degree, fourth degree, and fifth degree polynomials, I believe are new for you. I don't think you guys have ever seen anything this complex in any of your previous math classes. The name of a third degree polynomial is called a cubic polynomial, and that one is going to have an x raised to the third power. So it might look like x cubed, and then there can be other terms underneath it. So if I filled everything out here, there'd be an x squared term. So again, I'm just making things up here, minus 4x squared, and then maybe plus 3x, and then there could be a constant at the end of minus 1. Now, what I want you guys to notice real quick, a 0 degree polynomial, a constant, can have one term. A first degree, a linear, can have 2 terms. A second degree can have 3 terms. And a third degree can have up to 4 terms. So if I ask you how many terms a fourth degree polynomial can have, you'd probably correctly guess that the answer is 5. But the important thing I want to get across, guys, it doesn't have to have 5. So let me show you what I mean. The name for a fourth degree polynomial is a quartic polynomial there. And that one has x to the fourth power. So it would have to begin with x to the fourth, but it doesn't need to have every single term that comes underneath it. We don't need to have an x cubed. Maybe we jump all the way to an x squared term and go with something like plus 5x squared. And then maybe I'll have an x term right there, like minus 6x, and it doesn't have to have a constant at the end. There you go. That quartic polynomial only has 3 terms. And lastly, guys, a fifth degree polynomial, fun word right here, is called a quintic polynomial. These two words right here, guys, not overly important right there, but we better know what quadratic means. I hope you know what linear and constant means, and we should know what cubic means going forward. An example of a quintic polynomial, it would have to have an x to the 5th term, so I'll just throw a coefficient there of negative 2x to the 5th, and maybe this one just has a, I don't know, a minus 7x cubed and then a plus 13 at the end. There you go. That would be an example of a quintic function. It could have up to 6 terms, but it doesn't have to have that many. Okay, so some of the first homework you're going to see in this chapter now, guys, is going to give you a polynomial function like this and ask you to do a couple of things with it. I just remembered, I said I would come back to this concept right here from the first slide. If they ask you to put it in standard form, this is what it looks like, guys. P of x is equal to, okay, blah, plus blah, plus blah, plus blah. Okay, here's what I want you to realize. You start off with your highest exponent, which we're just calling n, and then each subsequent exponent is one less than the one that came before it until you get to this k term at the end, which has no x's. That's your constant. So real quick, guys, if you want to know what standard form of a polynomial means, it basically means you're supposed to write that polynomial in descending order according to powers of x. So make sure you guys know that. Standard form means descending order. Now, I think I've done a bad job here because descending order, oh, nope, I was on the right slide, is normally the way we write our polynomials. So if we take a look at this first one right here, first ask yourself, is it in descending order? X cubed x to the first, and then no x's at all. Yeah, so this one is already in standard form. So if they ask you to do that, no need to do anything right here because it's already done. Okay, what's going on, guys? They're asking for the degree of this polynomial right here. So you're looking for the highest exponent that you can find on your variable. X to the third, this is x to the first power, and no x at all. So this 3 right here tells us that this is a third degree polynomial, and the name for that we want to get used to is a cubic polynomial. Now, in terms of type, what that really means, guys, is they're asking you for the number of terms. And here's a word you guys probably know. 1, 2, 3 terms right there tells us that we are dealing with, there's the phrase trinomial, which is a phrase I'm hoping you guys are familiar with already. If monomial meant one number or one term, trinomial means 3. And of course, I've skipped right over the most common one, which is binomial, which means 2. This concept right here, leading coefficient, seems really, really easy. When you hear the word leading, you initially think out in front, and a coefficient is the number out in front of a variable. So in this case, you're going to be tempted to look at this expression and say that the answer is 5, and you're right in this case, but let me explain why. Leading coefficient doesn't necessarily mean the first number. It means the coefficient of the highest degree term. Now, since x cubed is the highest degree term, that makes 5 your leading coefficient. So it will be the number out in front if your polynomial is in standard form. But as you're going to see on the next example, that's not always the case. All right, let's look at B here, guys. G of x equals, and I got a little messier now, 11x minus 4x squared plus x to the 5th over 3, and then a minus 13. Degree, we're looking for the highest exponent you see on your variable, and that comes right here, guys. So this is a 5th degree polynomial, and the word we'd like to get used to for that is quintic. Fun one right there. Okay, the type of polynomial, just count your terms. 1, 2, 3, and 4. We don't have a cool name for a 4-term polynomial. If anything, we would go, let's see, monomial, binomial, trinomial, quadrinomial, if we were going to use a Latin root, or maybe tetranomial if we were going to use a Greek root. But all we do here, guys, is we just call this a 4-term polynomial. We kind of get lame here after 3. After trinomial, we just name it by the number of terms. So this would be a 4-term quintic polynomial. And now, this is the one I wanted to talk about here with you guys, your leading coefficient. A lot of people are going to tell me that it's 11, but that would only be true if this polynomial were in standard form. This one is not. It's not in standard form because we're not in descending order. So the leading coefficient, let me say again, is the coefficient of the highest degree term. This is a 1st degree term, 2nd degree term, 5th degree term, and a constant, a 0 degree term. So this term right here, guys, is the highest degree term that we have. And our leading coefficient would be the coefficient of this term right here. So I would ask you guys, what is that x to the 5th being multiplied by? Well, a lot of you are going to say it's really not being multiplied by anything. It's being divided by 3. True, but let's go back to 7th or 8th grade math, guys. Hopefully you learned this. Dividing by 3 is the same thing as multiplying by 1/3. So with a 3 on the bottom, we would say that your leading coefficient here is going to be 1/3. And I wanted to hit this concept of leading coefficient because that's going to come in play and be important later on this year, guys, when we start talking about horizontal asymptotes in rational functions. And I'm sure when we get there, you'll remember everything we talked about right now. Okay, so what are we going to do next, guys? One cool thing about polynomial functions is they all follow certain rules for what we call end behavior. They all do a certain thing way off on the right, and they all do a certain thing way off on the left. So here's what we're going to write for end behavior, guys. In all polynomial functions, and we do mean all, as x approaches either positive or negative infinity, f of x, and let's remember, guys, that f of x is just your y value, also approaches either plus or minus infinity. Okay, what in the world does that mean? Every polynomial, no matter what it looks like, and we're going to see some interesting shapes, on the right side, they all either go up towards infinity or they go down towards negative infinity. And on the left side, they either go up towards infinity or they go down towards negative infinity as well. But polynomial functions don't do things that other functions sometimes do, like kind of hover in the middle with a value like this. Polynomials won't do that. They're either going to take off and do that towards infinity or come down the opposite way and go towards negative infinity. Now, what we're about to go through here, guys, it scares people a little bit at first. It really shouldn't, because there's actually going to be kind of a systematic way that we talk about how to do this. So what's going on here, guys? We're supposed to describe the end behavior for this function right here. F of x is equal to negative 2x squared. And I started you guys with one that you should already know from chapter 4. Negative 2x squared is a parabola with its vertex at the origin opening downward. It's skinnier than normal, but that's not really important right here. This is a rough draft, a rough sketch of what this function actually looks like. So what's going on here, guys? They're asking us two questions. As x approaches infinity, positive infinity, which means as we move further and further out to the right, going this way, what happens to our y value? Now back to what we wrote down on the previous slide. As x approaches infinity, y approaches either positive or negative infinity. So you guys just need to ask yourself, as we move further and further to the right on this graph, let me take a big red dot right here and see if I can move it. As I move this thing further to the right, am I going up towards infinity or down towards negative infinity? And the answer to that is we are heading down towards negative infinity. So as x approaches infinity, y approaches negative infinity, because this graph goes down on the right and not up. How about as we move the other direction now? As x approaches negative infinity, so I'm moving this red dot from right to left, our y value is approaching. Is it going up or down? It's going down again. So y approaches negative infinity as well, because we're moving down on the left also. So that's your first end behavior problem. Now, it's not always going to be as nice as that. You're not always going to know what the graph looks like. So the way to really handle this, guys, is to think numerically about what happens when you put either a positive or a negative x value into this function right here. Let's think about what happens when you put a positive number in there. When you take negative 2 times some positive number and square it, let's think about what that means, everybody. A positive number squared, all we care about here is sign. A positive number squared is positive, but then we're going to multiply that by negative 2 and get a negative result. That's why we're approaching negative infinity. How about as x becomes a negative number? Negative 2 times a negative number squared. Well, you'll take that negative number squared and it will become positive. But then you'll multiply that positive times negative 2, it becomes negative as well. And that's why as x approaches negative infinity, y approaches negative infinity as well. All right, let's see that contrasted with something that's going to happen here. Shoot, and I just ran out of room here, guys. Let's slide that. My spacing gets a little weird when I switch this over onto the iPad. Sorry, there's a minus 2x there at the end. That's what this was. But actually, that leads right into the first thing I was going to say. The good news for us is, guys, when we're talking about end behavior, we don't care about these more minor terms right over here. They matter when x is small, but they don't matter when x is approaching a huge number, like towards infinity or negative infinity. So this is the only number, the only term in this polynomial that we care about when we're talking about end behavior. Now, by the end of this section of notes, we're going to start doing some graphing with what are cubic functions right here, but for now, you don't know how to do that. So let's go ahead and talk about it the way we did just a second ago. What happens when we put in a positive number as x approaches negative infinity? We're looking at this term right here, guys. So it's 4 times a positive number to the third power. Let's think about what that does. A positive number cubed. Positive times positive times positive is positive. Multiplying that by positive 4, that result is positive as well. So that means that as x approaches a positive value, our y value is approaching positive infinity. This thing is going up on the right. That's what that means. And now what happens when we let x approach negative infinity? That would be 4 times a negative number to the third power. And let's think about that. A negative number cubed, negative times negative times negative is negative, times 4 is negative as well. So as x approaches negative infinity, y is approaching negative infinity also. That means that our function is going to go down on the left. Now, as we'll see a little bit later on in this chapter, this polynomial function probably looks something like that, and that kind of supports the ideas that we came up with here and here. A couple more quick examples. Hopefully we're starting to get the hang of this. Now, what about when f of x equals negative x to the fifth minus 2x squared? Once again, the only term we care about is the highest degree. This term here becomes irrelevant as x is approaching infinity or negative infinity. So let's think about what happens when we put a positive number into this term right here. The opposite of a positive number to the fifth. A positive to the fifth would be positive, but the opposite of that would be negative. So our first end behavior here, negative infinity. As x approaches positive infinity, y becomes negative and approaches negative infinity. How about right here? If we put in a negative number into this term up here, it's going to be the opposite of a negative number to the fifth power. What's that going to do for us? A negative number to the fifth, because it's odd, will be negative, but the opposite of that negative number will be positive. So as x approaches negative infinity, y is approaching positive infinity. So what did we learn here, guys? This right here tells me that as we go right, this graph goes down. So we're going to be hitting down here somewhere. But now, as x is moving to the left, y is going up and approaching positive infinity. And this graph might look something like, and again, I'm just eyeballing right here of what a fifth degree function can look like. We'll get into that later. Might look something like that. Up on the left, down on the right. One more, no, I lied. That's the last of those examples we're going to do. So I'm going to go ahead and stop this video right now, and then I'm going to come back and show you how we're going to do these last two problems of graphing polynomial functions in part 2.